And we are here for the second part of the Nitro Whitepaper walkthrough. We previously had Lee, Rachel, as well as Daniel G, another one of our engineers. I should call them wizards, actually, wizards in technology, walking through the white paper and giving us like a good idea of like kind of what our new tech stack essentially Nitro is. Today we're going to kind of continue that, as well as maybe do a little extra things that whatever Lee and Rachel essentially decide to do on the Nitro front. With that being said, I'll hand it off to y'all. Go for it.
All right. Here, Hunter, if you could bring up my screen share. There we are. So, continuing the Nitro white paper, last time we got through most of it. One section we didn't get through is the AnyTrust section. So, as you may know, AnyTrust is the technology that we built our Arbitrum Nova chain on. So Arbitrum Nova is the chain most known for Reddit, but with other projects deploying on there too. And the reason why we have two chains, Arbitrum 1 and Arbitrum Nova, is that Arbitrum 1 posts all of its data to Ethereum. And that has both upsides and downsides. The upside is security. Because we're posting all of our data to Ethereum, obviously everyone trusts Ethereum. It's I think I can safely say the most trusted smart contract layer 1, which is why we started by posting all of our data there. But for Arbitrum Nova, we've assembled our own data availability committee, and you can read about its members online. It's quite impressive. But because we're posting data to somewhere other than Ethereum, Arbitrum Nova has the additional security requirement of you have to assume that at least, I believe, 2 of the data availability committee members are honest. And in exchange for that small sacrifice of an additional assumption, what we get is a lot cheaper data, because especially right now before EIP 4844, posting data onto Ethereum is quite expensive. And it's much cheaper. We can instead post data to a committee that we assemble and we built specifically for storing data. So that's what AnyTrust allows you to do. It keeps the actual the optimistic proving strategy is the same, but the data comes from a separate data availability committee member instead of Ethereum, and that's what makes Arbitrum Nova even cheaper than Arbitrum 1 already is. So with that overview, let's get into some specifics. So let's see.
I guess one thing I'll add about it is just a little bit on that like security assumption here. So, you know, in most systems in blockchain, right, like you need a supermajority or, you know, 2/3, 51%, something like this to ensure the correctness of the protocol. And in our case, the part of the protocol we're really thinking about here is data, right? If I want to submit a fraud proof, I need to have the data over which that proof, you know, happened and stuff. So you need that to construct a proof. Now, it's interesting, right? In this model, you need an honest minority. So there's kind of a few different scenarios. And how this is basically achieved is in the case where that minority is honest, but the majority isn't doing things properly, we fall back into roll-up mode, as we call it. So essentially, we go and use the same strategy that Nitro uses on Arbitrum 1, or just pure Nitro uses on Arbitrum 1, where like you're posting the data to Ethereum itself. So the idea is like, you know, in the happy case, the committee does everything functionally. People's nodes aren't offline. People are, you know, behaving accordingly. But in the unhappy case, right, we go and say, okay, instead of putting the data in the committee, let's go put the data on L1. And if the data is on L1, you're A-OK. And if you can get the data from someone, you're A-OK as well. That's why you need 2 people to be, or that's why you only need a minority to be honest. Someone has to be out there who'll give you the data. Now, why 2 we'll get into in a second, but that has to do with like redundancy reasons. But and the fact that like how we actually achieve the happy case with n-1. But we'll talk about that in a second. Essentially, there's kind of like 2 cases of failure. One where not everybody's there, in which case, we're kind of like back in Nitro world. Everything's going to be priced like Nitro. You pay more for call data, but it still is correctly advancing. And then in the unhappy case, where you have to actually go and, use the and then in the happy case that you get to go faster. So that just adds a little more color to the trade-off there. But it's a very minor one because, if you look at the teams on it, you got Reddit, FTX, a lot of great people. If you just trust two of them, you've got your data.
Well, yeah, so that's what, as Rachel was saying, that's what makes Arbitrum Nova, one of the many things that makes Arbitrum Nova so innovative is it's groundbreaking in that it's only an honest minority instead of an honest majority, like most chains. You have to, your trust assumption is much, much lower than for other networks where you need to trust a majority of the participants. So how we actually do this is all outlined in the white paper, which we'll continue getting through. So one of the first things are what we call key sets. So a key set is basically a list of public keys for each of the data availability committee members. It has a BLS public key for each of them and the number of signatures required. And BLS public keys, you might have heard a bit about these with Ethereum too, actually, or Ethereum consensus. BLS public keys are also used there for a very similar reason to why they're used in Arbitrum Nova, which is that if you have two different BLS signatures of the same message by different signers, you can aggregate those signatures and combine them into one signature, which represents both the underlying signatures. And you can repeat that process. So you can take a bunch of different individual signatures of the same thing and combine them all into one big signature, which represents a quorum of the underlying participants. So that's why BLS is used here in comparison to ECDSA, which is what's used for normal signatures in Ethereum. Because when you go submit your transaction in Ethereum, normally only you have to sign off to it. But with Arbitrum Nova or with a lot of different consensus mechanisms, a lot of people have to sign off on the same thing. And that's where BLS is so powerful. And that's why we use BLS. So to recap, these key sets describe who's on the committee, what their keys are, and how many of them are necessary to sign something. And then these are managed, the key sets are managed on layer 1, and the sequencer inbox will, before allowing a batch to be posted, it'll verify that that key set is authorized to post the batch. In other words, making sure that the data availability member is authorized to sign for this data to attest for it. And then as for what's actually submitted to layer 1 Ethereum, that's what we call a data availability certificate. And that contains a few different useful things. It contains the hash of the actual data, but remember, we don't post the full data to Ethereum, we just post a hash of it. We also post the expiration time, which is important so that the sequencer couldn't do something malicious by attempting to hold back the data certificate for a long time and then posting it later. And then we also post a signature of all of the different committee members. And these committee members say, these committee members each have we have a different bit for each committee member, which indicates who signed it. And then we have a single aggregated signature of all of the different committee members. And that's, again, where BLS comes into play, because BLS lets you take all of those different individual signatures and aggregate them into one cheaper signature, because we want to post as little as possible to layer 1 Ethereum.
Now, you might be wondering, why is it like that you have to trust 2? Well, the thinking here is like this. In order for a batch, a certificate that is, to be valid, it needs to have been signed by N-1 of those participating in the data availability committee. So you need N-1 of them, whichever N-1, it doesn't matter, just as long as you have that to attest and make the statement, I have retrieved this data. I will give it to you if you ask me for a fraud for it during fraud proofs later. And the reason we do N-1 is to allow a stage of redundancy. Maybe there's an honest data availability committee member who, is just offline or, has some problem or something. If that's the case, it's say, okay, the chain can continue running with low fees using that. And that's why you don't want to require all of them, because if anyone has any issues ever, right, then all of a sudden you're back into roll-up mode. You're doing very expensive transactions. Well, not very expensive when compared to, Ethereum, but expensive in the sense of you don't want to have to pay for call data, right? Not in this regime. So you that's why I do N-1. And because it's N-1, you have to think about it like this. How many must be honest in order to guarantee that one of N-1 is honest? Well, that's 2, right? Because if there's 2 honest people, one of them might be left out, but that other one that's honest must necessarily be in that N-1 group that's required. So that's why it's that. We could have parameterized this system in any arbitrary way. We could have said, no, you need N-3 to do a signature batch, in which case you would need 4 to be honest, right? 3 left out, 1 in the batch, or rather, I should say data availability certificate. But we just thought that 2 was a very good level. And you can kind of just think about it in terms of it being this very small minority in a much larger group. Theoretically, if we had 1,000 people on the committee, you might say something like, you can drop 5 of them out or something, right? You pick the security trade-off that you think is good and the reliability trade-off with regard to redundancy, and that's how you select what makes sense. We picked 2, though, theoretically could change, but we think that was a very good choice for Arbitrum Nova. So that's why it has that specific number in -1 and 2.
Yeah. So on the next page here, we have a diagram of how the data availability committee member interacts with the rest of the system. And you can contrast this to a previous diagram we have, I believe. Let me see here. Where was that? Here we go, yes. So this is a diagram without the data availability member. This is how Arbitrum 1 functions. And then you can see down here that we added this data availability committee member, which happens after we make a batch and compress it, but before we post it to the layer 1 chain. So yeah, as we mentioned here, so with any trust, the sequencer can either post a data availability committee member, or if it's not able to do that, it can fall back to the layer 1 chain. The data availability certificate that it posts on chain will be validated by the layer 2 node. And the layer 2 node will verify that enough people actually signed the keys, or enough people actually signed this certificate, that this aggregated signature is valid, and that there's enough expiration time for any validators to be able to read this certificate in the future, basically. Now, the data availability certificate isn't verified at L1 because verifying a BLS signature on layer 1 Ethereum right now is rather expensive. So instead, what we do is we verify the certificate at layer 2, and then if it's invalid, all we do is we simply discard it and move on to the next block. And that means that we can save ourselves from having to do all of this expensive computation on layer 1, and optimistically we can do this computation on layer 2, which is one of the reasons why we don't have a bunch of additional costs from this scheme. Let's see. The data availability committee themselves expose 2 APIs. One of them to the sequencer, which lets the sequencer post batches, but only the sequencer is allowed to post data to the committee. And then the other API is for anyone running a node. They can go query the data availability committee member and look up what they can look up the data for a given hash. So that's how you can, from an inbox message, figure out what the underlying transaction data is. You go query one of these committee members and ask them, hey, do you have this data? Let's see. So what the sequencer does with that is basically it, whenever it wants to post some data on chain, the first thing it does is it reaches out to all of the different committee members and says, hey, can you store this data for me? And the data availability committee member, if it's working correctly, will say, yes, I can, and it'll go ahead and store it. And then it'll say, here's a signature showing that I've stored this data. The sequencer can then aggregate all of those signatures together and make one big signature that's posted onto the layer 1 chain. If enough of the committee members don't respond, if we don't have that threshold of n-1, then what the sequencer can instead do is it can post the data directly on chain. So instead of posting the certificate, it posts the full data, which again is a lot more expensive, but it does mean that we don't have to assume that most of the data availability committee members are honest, because we can fall back to roll-up mode, as we call it, fall back to posting the full data on chain. Let's see. So I think that's most of how the data availability committee member works. Do you have anything to add, Rachel, or we can move on to how compression works?
I think people would really like to hear about compression. We've given an overview to how data availability works. Yeah, that honest minority assumption's fun. And just the last thing I'll highlight on it, the only thing the data availability committee does is store data. Store and give it back if you ask for it. That's really it. It's not like the data availability committee's like doing like transactions or something. It's purely just for the ability to like save that stuff and not post it to L1. Very minimal security trade-off. If anyone in existence, right, has the data you need, then you're good. So like, theoretically, even if the sequencer had it, or if, your node did, and then someone wanted to ask your node for it, those are theoretically things that could be done. But really, it all comes down to that committee being honest, or at least one person in the committee being honest when n-1 have been chosen to post a batch. And now it's extremely common, right, for it to be all of them, right? All in can just say, hey, here's my, I've stored it for you. And that's the normal situation, because no one on the committee is like dishonest, it seems. But, you don't have to trust in that. You can just trust that 2 of them are, and then you get all the properties you want.
Yeah. So to get into how our compression works, our compression is one of the it's one of the really nice things about Nitro that we weren't able to do in Arbitrum Classic. So we'll come back to the data availability committee the data availability committee in a second. But let's for a second look at how Arbitrum 1 works without a data availability committee. So what happens is these transactions are sent to the sequencer. The sequencer, through a feed, says, here's what order I'm sequencing these in, and all of the nodes can get that ahead of time. And then eventually what it will do is it will batch up all of these sequence transactions into one batch and then post that batch to layer 1. One interesting thing is that the state transition function here, which determines these L2 blocks, doesn't actually depend on the compressed data, it depends on the uncompressed data. So how a node might look at this is it might, from the layer 1 chain, pull up the batch here, and then decompress it into these sequence transactions, and then run the state transition function on it. But what the sequencer can do is it can simply run the state transition function on the sequence transactions before compressing them. So why does this matter, right? Well, in Arbitrum Classic, before we upgraded to Arbitrum Nitro, the state transition function depended on the actual compressed transactions. And why that's an issue is it means that the sequencer could only compress one block worth of transactions because the outcome of a block would depend on how it's compressed. So you can't compress multiple blocks together. You wouldn't know what the output of the first block was. So what the sequencer needed to do in Arbitrum Classic was make a block, compress the transactions in that block, and post it to layer 1. But one thing about compression is compression gets better the more repeated data you have. And in a single block, you might not have that much repeated data. But for instance, if everyone 5 blocks in a row is like doing a Uniswap trade, for instance, compression can then look at that and see that there's the same Uniswap address in all 5 blocks. And then instead of repeating that data, it can refer back to that data only once. So to summarize here, compression is better when it operates on more blocks. And that's what the new design allows this system to do. Because the sequencer can know what the outcome of a block is going to be without caring about how those transactions are compressed, it allows it to compress a much larger set of transactions. And in Arbitrum Nitro, we compress a whole batch, which could be like 5 or 10 minutes worth of transactions. And we compress all of those together, which is one of the reasons why Arbitrum is so cheap post-Nitro. We've talked a lot about how fast Arbitrum Nitro is, which it is. But another benefit of it is this detail of how compression works is why we're able to make the L1 fees so cheap, even when you're not using Arbitrum Nova, where they're even cheaper. And then with Arbitrum Nova, what we do is we take this compressed batch, and that's what the data availability committee has to store. They store this compressed batch here. And once again, this means that if the sequencer has to fall back to rollup mode, this doesn't actually mean that there's a big reorg. In Arbitrum Classic, if we had designed data availability committee data availability committee on Arbitrum Classic, falling back to rollup mode might have meant we'd have to like redo a bunch of chain history and it would be this big mess. But with Arbitrum Nitro, the really nice thing is that the blocks only depend on the transactions within. So we get the nice property if we can change how we post the data to layer 1 without it affecting the layer 2 blocks. It's transparent. We can post the data in any format we want to layer 1 without changing what happens on layer 2. And that's what that interesting property of how Arbitrum Nitro is built is both what allows us to offer such cheap layer 1 fees on Arbitrum 1 and to make Arbitrum Nova able to fall back to the rollup mode by posting the full data to layer 1.
Yeah, so that's pretty comprehensive on how the compression works. And as we talked about last time, we have the ability to prove arbitrary WASM code. And like the compression scheme itself is just a program. It's the official Brotli implementation. And we just link against it, compile to WASM, and now we're able to use it like we would anything else. I think this actually shows some of the this is definitely demonstrative of the generality of our proving system and like the fact that just everything's very plug and play and it all just works. And yeah, with very minimal linking, we were able to just have this very efficient way of compressing. And yes, by the way, that's the compression algorithm we use. We use Brotli. We profiled a bunch of different ones, but that seemed to have the characteristics that we were looking for. And it's been quite performant. I mean, the fees have been really low. If you actually, if you check L2 fees, you'll commonly see that like swaps and stuff are just so inexpensive. And I remember things that used to be like $1 are now commonly measured in cents or even less of that, or even less than that. So yeah, we've talked a bit about compression. I don't know if there's anything else we want to say here before moving topics. Lee, what do you think?
There's one other thing I wanted to mention talking about generality, which is a lot of people, when they hear that like there's a fraud proof, what they might expect is that there's a fraud proof showing that a data availability certificate is invalid. But actually, we're kind of like there's a level of abstraction missing in that thinking. It's not really that we show that the data availability certificate is invalid. It's that we show the correct execution of the Arbitrum chain would be to ignore that certificate because it's invalid. So why is that so important, right? Well, it's important because in our proving code, we don't actually have a issue a proof for bad certificate. We don't have to special case every type of thing that could be wrong and have a new proof for if this transaction signature is invalid or if this data availability certificate signature is invalid. All we do is we have a proof for how you execute a WebAssembly instruction, and we build that simple proof of executing a single WebAssembly instruction. We combine a ton of those, and that makes up the Arbitrum chain. So instead of proving some fact like a data availability certificate is correct or incorrect, what we end up disputing the proof down to is we'll narrow down where the issue occurs, and we might narrow it down to the part of the code that verifies a BLS signature of the data availability certificate, right? But we'll narrow it down even further. We won't just say, hey, the signature is invalid. We'll narrow it down to an individual addition that makes up the cryptography code that validates that BLS signature. And we narrow it down that much such that we're not disputing a signature. We're actually disputing a single addition. And that's the reason why our proofs are so general. We can write pretty much anything we want. We can take any Go code and we can prove it. So when we went to go add the data availability committee, we didn't have to change how our proving worked. All we had to do is at layer 2, in our Go code, we just had to import an existing BLS library, the same one I think that Go Ethereum uses, and use that to validate a signature, which is one of the unique benefits of our proving system, is that it is this general, essentially.
Yeah, you can essentially think of it as what would the code do at this step? That's what we come to disagree on. And if the code says to only accept a signature that has N-1 participants, you'll get to some WASM instruction somewhere there that makes that disagreement happen. There's not this special casing where every single time we want to do something, we have to add some new thing. I've seen there's recently been some papers on, say, using the EVM itself as the proving vehicle. But the problem with that is it's just too high level. You don't want to have to prove over things take self-destruct, right? That's very complicated opcode. Instead, you want to be able to say, agnostically, deep inside of Get's, VM for doing a self-destruct at this specific database thing, we come to a disagreement. It's so powerful. And it actually is we don't even have to be proving Go Ethereum. We could be proving pretty much anything. We talked about how last time it's even chain agnostic. Theoretically, we could take other VMs. We could take just anything that compiles down to WASM. There's not really a lot of stipulations on it, which is exciting. It's not like our old system where we had to write it in this special language. We're now able to just do arbitrary WASMs. So, as Geth makes changes, our fraud proof doesn't have to. As we want to add new features, new precompiles, again, fraud proofs don't need to change. We don't need to when a new precompile has been adopted that adds, say, BLS or some very fancy crypto curve or something. We don't have to go, okay, guys, let's all come together, write a new ZK circuit, or come up with some new level of indirection. We've already got it all. If the thing can compile to WASM, which it totally can, if it's written in Go, Rust, C, or anything we really ever want to use, then we're good to go. So yeah, that right there is the biggest thing that Nitro has, but all these other subcomponents to it are then enabled to be written in these nice languages and nice with these nice primitives, and taking direct advantage of Geth at the core, as we say several times in the paper. Compression included, data availability computed, pretty much all of it. So yeah, that's all I'd really add to that topic.
Yeah. So let's see. We've got a question from the audience here. What's the difference between Arbitrum and Nova from a tech point of view or something? So I've gone over this. I'm not sure if you were here for the beginning of this stream, but the main difference, or the only difference, I should say, is that we have this data availability committee involved here. So if you look in the white paper, I believe figure 1 shows how Arbitrum Nitro usually works for instance, Arbitrum 1. And figure 3 shows how Arbitrum Nitro works for Arbitrum Nova. And the only difference here is that we have this data availability committee member here. And what that means is that instead of posting the data directly to layer 1 Ethereum, we instead post the data to the data availability committee member. And then all we post to layer 1 Ethereum is a certificate from the data availability committee that says, yes, we have this data. And that's what provides the security guarantees of Arbitrum 1 versus Arbitrum Nova.
We're taking audience questions too, by the way. So if anyone has them, please post them in chat.
Yeah. So let's see. We have a question about the difference between Arbitrum Nitro and Optimism Bedrock. Frankly, I haven't reviewed our Optimism Bedrock enough to give a fully qualified answer on that. I did see, though, that there's a blog post series by a third party which has been going into the differences, and it started on deposits. It's really cool. I'll see if we can put a link to that somewhere. But at the surface level, one of the main differences I suppose that people point to is that Arbitrum Nitro uses WebAssembly versus Optimism Bedrock uses MIPS. But fundamentally, my understanding is that it's largely a similar architecture, where Optimism has switched from their original goal was to do a single round fraud proof, and they've switched to our style of doing multi-round fraud proofs. So as far as I'm aware, it's kind of moving in the same direction. But again, I don't know the I don't know the specifics of Optimism Bedrock.
Yeah, and essentially to add some color to that, like Arbitrum, we've had fraud proofs on every chain that we've ever deployed. This has been the case, ever since the very beginning with Arbitrum Classic, as we're now calling it. Back then, it was just Arbitrum, right? Optimism doesn't have fraud proofs. They are trying to add that in Bedrock. Theirs are based on MIPS or whatever. We'll see if that comes out. But essentially, that's kind of where they're going. In the same way they've adopted our multi-round fraud proofs, they seem to be going in the same direction of taking Geth at the core and compiling it down into something that you're actually like a lower level representation you're able to contest over in a generic way. So there's that. Now they did use MIPS, which is interesting. We think WASM's better for a number of reasons that we've talked about in the past, but very briefly to go over it, like WASM is a WebAssembly standard. So I mean that is what it says, right? WASM, WebAssembly. And it's been written and designed and all the tooling for it for the most adversarial case ever, right? Which is like a web browser. You don't want it to be the case that like when you go on a web page, you get, fly-by hacked or something. And so there's just this really amazing infrastructure and all of this tooling and all of these, known constraints around it that, you'll find in less mature technologies you commonly don't get, right? Like, yes, MIPS has been around for a long time, but, nobody's building like really great runtimes in it, say. And an example of something we very recently released that's been super exciting for those running validators is our new just-in-time accelerated validator. So just-in-time compilation is a thing that's very common in WASM. So essentially, like, you have this program, and instead of like doing all your compilation ahead of time, like while it's running, you go and you like make improvements as it goes. That's super high level. Like you can go way deeper into the theory of that stuff. But really what I'm trying to say is that there exist these really powerful runtimes like Wasmer. And we actually wrote an update recently that cut the costs of doing fraud proofs down 90%, actually over 90%, where instead of having to invoke the more expensive arbitrator binary where you're like, doing the full fraud proof, using no acceleration, you're now able to use this JIT accelerator by just changing a flag when you start up your node, and it'll use Wasmer to actually go and do block by block integrity. So, when you run a block, you want to make sure that the result you get to in Geth is the same one you would get if you were to try and, do a fraud proof or what have you. And this validator we had, it used to take quite a bit of time for it to complete. But we can now do it like at over 8 billion gas a second, which is like faster than our speed limit. And, you only have to do that kind of stuff. That's, technically when you're engaging in fraud proof. But essentially what this means is that like you can be running full speed with very lower hardware than if you were like trying to go through some very expensive, pure WASM or pure MIPS thing. And I imagine this is going to be challenging for Optimism to do because, you can just know so much statically about a WASM program, and there's just these amazing tools and runtimes. It's extremely mature. And like, while it is the case that we have to do this like transpilation layer where WASM gets turned actually into an intermediate or into a representation we call WAVM. That's a technical detail you can read about in the paper. But even though you have to do that layer of indirection, you get from doing that the powerful ecosystem that WASM gives you. So I think that's another difference with it. Our gas pricing's all in L2. Like, we could like split hairs over various differences and stuff and, questions of technical debt or what have you. But I think essentially, Nitro is here today, and you can get those, advanced call data compression and all of that today, and do our fraud proofs today. So it's really cool to be this place with Nitro and what's coming next. So any other questions? I think there might be a few.
Let's see. There was one about Arbitrum Nitro 1 Nova. Yes, here we are. So one thing I'd like to clarify here is that Arbitrum Nitro is a technology. It's not a specific chain. So Arbitrum 1 and Arbitrum Nova are both built on the Arbitrum Nitro technology. And Arbitrum 1 was previously built on what we are now calling Arbitrum Classic, which used the AVM, the Arbitrum Virtual Machine, to execute a version of ArboS written in this mini programming language. We upgraded Arbitrum 1 from Arbitrum Classic to using the Arbitrum Nitro software. And the Arbitrum Classic software is no longer in use for any of our chains. Arbitrum Nova was started with the Arbitrum Nitro software and, of course, continues to use Arbitrum Nitro. So to recap here, we have two chains, Arbitrum 1 and Arbitrum Nova, and they both use the Arbitrum Nitro software. We plan on using Arbitrum Nitro into the future, but obviously if something better comes up, we'll switch to it as we've done in the past. As far as Arbitrum 1 and Arbitrum Nova coexisting, yes, Arbitrum 1 and Arbitrum Nova have fundamentally different security properties, which is why we didn't want to add a data availability committee to Arbitrum 1. We didn't want to change the security properties of a chain that everyone was already using. So instead, we introduced a new chain, which does have some additional security assumptions, but in exchange, you get way cheaper fees. So those two will continue to coexist. Let's see. Speaking of which, someone also asks, is Reddit the only beneficiary of Arbitrum Nova? No. We built Arbitrum Nova for anyone who was essentially priced out of Arbitrum 1. And Arbitrum 1 is already way cheaper than Ethereum. But for some applications, like gaming, for instance, it might not make, even though our fees are only cents, it might not make sense to pay cents, no pun intended, for like every time you do an action in a game, for instance. And it depends on the game, of course. But if Arbitrum 1 is still too expensive for your use case, we built Arbitrum Nova, which brings fees down to tenths of a cent even. And what that means is that in exchange for the Data Availability Committee security, you can do transactions even cheaper by posting data directly, or by posting data to the Data Availability Committee instead of layer 1. and that makes Arbitrum Nova a much cheaper chain. And that's not just for Reddit. We've already seen deployments of a lot of other applications on there, and I'm sure more will follow. I don't know, Hunter, if we have a portal for Arbitrum Nova, but if we do, we can maybe post links to that. I'm not sure.
Other questions on validation. Yeah, currently validation is whitelisted. So no, not anyone can do a fraud proof right now. We are expanding the whitelist, and we'll drop it. So yeah, the first thing we did was we wanted to release Nitro, get to that point. But obviously, just being cheaper, just being faster, those aren't the only things we care about. We also care about decentralization. And so, yeah, in the very short-term future, we will be making things better there. And, in the longer term future, of course, we'll also be, not to make it sound like it's too long, but we'll also be decentralizing the sequencer and just trying to take these components in the system and just, broaden it as much as we can. There's a lot of exciting stuff coming there. And I really, really look forward to it. And we want you all to be able to engage with the system in that way. But yeah, first step was getting Nitro up the door. And, with this really powerful proving technology, that is the most obvious next step. So, as well as continuing to work on lowering fees and stuff, we've also got stuff there too. We'll tell you about in the future.
Yeah. So to expand on that, Arbitrum 1 is still in a mainnet beta, and we are always working on all avenues of improving it, including improving decentralization, improving fees. One question I have heard is if we've seen a fraud proof. The purpose of fraud proofs is that you don't see them, right? But we're very careful to test them. So we have a number of tests that anyone can run, and verify that, and you can see our fraud proof system working. We have a test, I think it's the test challenge something, in our code base where you can see we set up two validators and we give them competing views of what happens. And then they fight it out on chain. And you can see one of them wins and one of them loses according to who's actually correct on chain. So this is very exciting for us because unlike a lot of other layer 2s, we actually have fraud proofs. And you can see this all working, and that's all live. So
and one thing to keep in mind about fraud proofs is they're fraud proofs. They're not validity proofs. So only in cases where someone actually commits fraud do you engage in them. And because it's kind of an interesting catch-22, right? Because in the normal case, people would say, oh, well, if I lie about the state of L2, I'm going to get slashed for it, right? So then you just don't lie about the state of L2. Well, then that means people don't submit fraud proofs because it doesn't make sense to do it, right? This isn't like a ZK model, say, where you need to make some attestation to, what happened. You give your validity proof, and then all of a sudden, everybody verifies that. That's not necessary. Instead, what we do is we see, oh my gosh, we have Nina. Yeah, hey, Nina. So that's Nina in chat, or in Hunter's camera. That's super dope. I don't know if they're able to talk right now. I think they're in a meeting, but
We can. I just don't want to interrupt you. I apologize.
oh yeah, you're totally good. Yeah, just wrapping up what I was saying there. Yeah, it's essentially so the point is fraud proofs, we test them, they work. You can spin up your own little system and play them out, the validators are running and all that with it. But it's just nobody's gonna start being malicious on Arbitrum 1 because you're gonna get slashed if you do it. So that's the first thing there. And then someone asks about programming languages and stuff. Yeah, Nitro and Nova, Arbitrum 1 and Nova were written with the Nitro code base. So our languages are, a lot of Go, because Go Ethereum, as the name would suggest, is written in Go. So we have that. Then we have Rust for a lot of our proving stuff, and compression, all that. Well, actually, our compression stuff too, we have C. So Brotli is an IMPL written in that. But the point is, all these things can be linked together and compiled down to WASM. So, theoretically, if we wanted to throw other languages in there, it wouldn't be a problem. We can just do that as long as it's possible to compile to WASM, which any language you would ever want to use, of course, could be. We can do it. So, yeah, that's all I have to say on that topic.
I think in the interest of time, we probably should wrap up. But obviously, if anyone has any more questions, you can always join the Discord. Make sure to link it in the chat, so you can like rack Lee and Rachel's brains a little more. They're really throwing the questions.
Yeah, we'll do another one of these. The VOD will be made public too on YouTube, I believe. So you'll be able to see this, especially if you join later. You'll still be able to view it. And we'll wrap up here, but this was really fun, guys. We'll do another one, and we'll be on Discord. So come join us there.